The question I have is, could you discuss the theory of one-dimensional flow in soil, including Darcy's law? What I have here is a one-dimensional flow setup, and you might ask, why is this one-dimensional, right? But I'll prove that to you a little later. I have a cylindrical tube here that has a constant cross-sectional area A packed with a little bit of soil in there. The setup that you see in this graphic is used to induce flow through the soil packed in that cylinder. One vertical tube is attached to the bottom of the cylinder, and the second one is attached to the top of the cylinder here. And we are maintaining two different levels of water in these tubes, higher here and lower here. The difference is delta H. Let's consider 2 points, point A at the lower end of the cylinder, point B at the upper end of the cylinder. Let's define a reference elevation called datum. With respect to this datum, the elevation of point A is ZA and elevation of point B is ZB. The height of water at point A is YA and at point B is YB. Even if the soil is not fully saturated initially, it's going to eventually become saturated. Once the flow becomes steady, the rate at which the water flows through the cylinder is going to be constant Q. And you will find that that is the rate at which you need to supply water here, and that is the rate at which the water will come out of this cylinder here. Now let me define the total head at point A, H sub A. You might recognize this equation from your fluid mechanics class. And sometimes this is called specific energy, but we'll call this total head. And here VA is the velocity of water flow at point A, PA is the pressure at point A, and ZA, of course, is the elevation of point A with respect to this datum. So there are three terms in here. The first term is called the velocity head, the second term is called the pressure head, and then the third term is called the elevation head. It turns out that for most problems that we deal with, the velocity head is negligible. The velocity of water flow inside these tubes is also negligible. Then basically the pressure at point A is the hydrostatic pressure at point A, which is given by this equation, and therefore PA over gamma W is simply equal to YA. Then the total head at point A simplifies to this equation right here. Similarly, the total head at point B is written like this. Now if you come back and look at the picture one more time, you notice that this whole distance starting from the datum to the top of the water level is the total head at point A. And similarly, this distance starting from datum to the top of this water level is the total head at point B. They are not the same, higher here and lower here. So here's an equation giving the difference in heads. Now we define what is called a hydraulic gradient like this, where delta H, as you already noticed, is the head difference between points A and B, and L is the distance between these 2 points. Little I is the notation that I will use here. Now we are ready to talk about Darcy's law. Darcy found out that the velocity of water flow from A to B is proportional to the hydraulic gradient. Now we can turn this into an equation by inserting a constant of proportionality, and this constant of proportionality is what is called the permeability. So this is basically the constitutive law pertaining to water flow problems, just as Hooke's law is the constitutive law pertaining to the solid mechanics problem, right? Remember, in linear elastic problems, Young's modulus relates the normal stress to normal strain, and similarly here the permeability relates the velocity to the hydraulic gradient. So this is a property of the soil, and this is perhaps the most important property in water flow problems, and we'll talk more about this a little later. Some observations. We know the dimension of the total head is length, right? And therefore, hydraulic gradient is a dimensionless quantity because you are dividing length by length again. And therefore, coming back to this equation, we can see the velocity and the permeability must have the same units. So, for example, it could be meter per second or foot per second or centimeter per second and so on. The Darcy's law also tells us that when the hydraulic gradient is zero, which of course occurs when delta H is zero, V is zero, and therefore there's not going to be any water flow through the soil. We also infer from this equation that when HA is greater than HB, delta H is going to be greater than zero, and therefore IE is going to be positive, and therefore water flow is going to be taking place in this direction. And vice versa. In other words, when you have a higher head over here than here, water flow is going to be reversed. Here YA and YB are referred to as piezometric heads. And if you want to find these in the field, for example, all you have to do is to go and insert thin tubes at these points, and then the water will rise to through a distance equal to the piezometric head. Like, for example, at point A, if you insert a tube, water is going to rise up to this level right there. Finally, I also want to point out that it's not the elevation head alone or the piezometric head alone that induces water flow. It's a combination. It's a sum. There has to be a difference in the sum. Let me take a simple example. I have a tank full of water here, right? I'm going to take 2 points, point A and point B, and prove using Darcy's law that there's not going to be any water flow from point A to B, which is a result we know. There's, water is not flowing from A to B, right? All right, so I'm going to define a datum here, and let's just say this distance from here to here is B1, from here to here is B2, right? And then we go ahead and define the total heads at these 2 points. At point A, the elevation head is B1 plus B2, and YA, the pressure head, is 0 because this is exposed to atmospheric pressure. And therefore the total head at point A is B1 plus B2. And if I now take point B, this is the elevation head, and this is the pressure head. So the sum again works out to be B1 plus B2, and therefore there's no difference in the total heads between point A and B. And Darcy's law say there should be no flow from A to B. On the other hand, if I come and punch a hole at point B, right, immediately this point is now exposed to the atmospheric pressure. And so now we go through the analysis. We find the total head at point A, which works out to be exactly same as before. Here we got B1 plus B2, and here too we have B1 plus B2. But at point B, we suddenly lost the pressure head, all right? So the elevation head is B1, but there's no pressure head. And therefore, HA is greater than HB, and according to Darcy's law, water is supposed to be flowing from point A to point B, which we know is exactly what is going to happen. But an important point to note here is that if we just consider only the pressure head, there is a difference between the pressure heads between point A and point B, and there should have been a water flow, but it's not happening. There's also a difference in the elevation head between point A and point B. Water is not flowing. So it's not the individual heads, but it's the total head, sum of the two, that dictates whether there's going to be water flow or not. I promised you earlier that I will come back and prove it to you that the flow condition involved in the earlier setup is one-dimensional, right? So let's go ahead and do that. So what I have done here is that I have drawn the lower part of the setup to an exaggerated scale for clarity. I'm going to take 2 points, point 1 and point 2, on the lowest cross-section of the cylinder here. The total head at point 1, H1, equals z1 plus y1, geometrically this length right here, and the total head at point 2, h2 equals z2 plus y2, geometrically this length right here. So from this you can see easily that h1 equals h2. According to Darcy's law, there cannot be any flow from point 1 to point 2. If I were to define a coordinate system involving x prime and y prime axes, like shown in this picture here, the flow therefore takes place only along the x prime axis, not along the y prime axis, and therefore the flow is 1D. In other words, the flow takes place only in that direction. There is no flow across the cylinder.